All right. Thanks for the introduction. Thanks for the invitation. So maybe not all of you have to respond, but in case no one hears me, which would be difficult to actually react on, then let me know. Okay, or if the audio is not ideal or whatsoever, try to fix it. So I'm responsible for the other half, which is non-commutative geometry, the other half of the theme of this workshop. And so that's a great pleasure, of course. It's already, we saw an intriguing introduction to topological recursion already just now, and then also try to kind of work towards that, to work towards the same models, at least, that we find in non-commutative geometry. But first of all, I would start this lecture with just some kind of motivating introduction, motivation and intro to what I will abbreviate as NCG. It actually captures the title of this conference is something like NCG and TR, so that's very good. And this will be based on spectral geometry. It's like a spectral approach to geometry that we take. So in case you're familiar with that, then just maybe sit back and relax. And then for the second the second lecture, tomorrow I will work towards how to build models, how to get models that you might be familiar with from non-commutative geometry. So this is about gauge theories from non-commutative geometry. And then, of course, there is a long story about standard model physics, particle physics, and one can talk a long time about this. But I would like to kind of work towards kind of first the basic principles, and then work towards these models that that you have now already seen in the first lecture this morning, which is like matrix models. So these kind of models I would like to kind of emphasize on in the examples that that I will be given. And they also will come back in some of the talks this week, actually the ones built specifically from non-commutative geometry that will actually be tomorrow, I think, with Lisa Glaser and Roberta Isepi. So they will be specifically built from within this, this context. And in the third lecture, I would like to actually complete the story by introducing sort of an action principle, a spectral action principle, which is spectral. So that's the main point. So it's an invariant that's not only kind of unitary or gauge invariant, but it's a spectral invariant. So it actually comes back to the motivation I'm giving today about that we try to capture geometry, all of geometry, by means of spectra. So spectral approach to geometry. And so in line with this, also the action principle, so that's like the minimizing action principle should be spectral. And we will see that that if we apply this to these gauge theories that describe matrix models, or are supposed to describe matrix models, then actually they do. And if time permits, but that really depends on how we progress, I can give you a little bit more about the structure of these spectral action. And so just to kind of give you some bit of connections to the literature. So for one thing, there's a book which I wrote with Springer. It's an introduction, so that's quite helpful, and it contains references to kind of previous books. For instance, the book on non-commutative geometry by its founder, Alain Kohn. So, but this one here is kind of a gentle introduction, starting without too much functional analysis, and that's NCG and particle physics. But to find it, so first of all, a draft and an updated draft is available on my website, which is here depicted written below. And if it doesn't work, then you can always email me. You can always send me a message if you have a question about the contents, of course. Another source could be noncommutative-geometry.nl. In particular, it contains the non-commutative geometry seminar and a lot of recorded lectures that appear there.
that you can just watch if you wish and have more background. Because of course I have 3 hours here, so that's not much, and it's actually perfect like this, because it's good to kind of give an introduction which is not too long. So that's I think the sources, and as I said, there's a few talks later this week that will actually connect very well to what I'm talking about. And I hope, of course, that this bridge that you're trying to kind of to get to with the topological recursion will also be supported by this this mini course. All right. Let me then see if I forget anything here. That's all right. So let me then try to go to the second page. Yes. So now you should be looking at some guy, which is Mark Kac actually. And this comes to what I alluded to before, is this spectral approach to geometry. And the key idea is that that you try to kind of capture geometry by means of a spectrum. And that spectrum in this case would be the kind of auditive spectrum. That's kind of course, the phrasing that Mark Kac used. Can one hear the shape of a drum? Which you might be familiar with, of course. More precisely, the idea is that that you start with a geometric space, which for us would be a Riemannian manifolds, which for convenience I take to be compact, but if not, then one has to wonder maybe about some boundary conditions or what happens at infinity. But in principle, the question can still be asked. And drums are typically compact, so that also helps to connect to this this problem. Compact, say, without boundary, so that's also good to keep in mind. That's my use of the word compact. Then the question is that, okay, you try to listen to it. That means you try to have kind of waves described by a Helmholtz equation, which is a Laplacian on M, which exists because it's a Riemannian manifold. So there's some metric, G. And then you try to solve this equation, where K are so-called wave numbers. Of course, this is very elementary. So you have this list of wave numbers, and the question is, so I could come from M and I can try to solve this Helmholtz equation. It might be difficult, but in principle it's possible. Now I ask the reverse question. If I know these wave numbers, this list of K's, they're just numbers, real numbers. If I know them, can I go back to M? So reconstruct the geometry M, G, okay? So is it possible to reconstruct? So that's the kind of mathematical phrasing of this question, can one hear the shape of a drum? All right, so let's look at some examples. It will be very mild, this introduction to start with. So let's look at some basic drums that I would actually play. I'm a percussionist myself, so these are the typical drums I use to play. So that's a disc. Of course, then there are some boundaries. So these are just for kind of illustrative purposes. So this disc can vibrate in 2 modes. Well, it can vibrate in any mode, but these are 2 examples of modes. And if you list, for instance, the first 200 of these wave numbers, so these are the numbers K that appear here, then I just list them in increasing order, then I find this sort of parabolic shape. Okay, so that's something that you can actually solve, and you can do the same for a more kind of rare drum, which is a square. It's still possible, and then you have these, of course, these boundary conditions that set the boundary to have a 0 solution, and then the wave numbers are again depicted like this, similar parabolic shape. But if you remember from the previous slide, it's already different. So the conclusion here is that at least if you know you're playing a circular drum or a square drum, then you can tell by listening to it which one of the 2 it is, because these wave numbers are just different.
Okay, that looks promising for Koch, but in fact, it's not the answer to his question is actually no, because it's possible to construct drums, the ones that you see here down the bottom. So these are the kind of what was written in with the.
Sorry, Walter, I have a question.
Yeah, go ahead.
So in your two examples, what exactly was different? I mean, can we see it on the graphs that you plotted? Something specific?
Yeah, let me flash it to you, so you can just look at the graph, and you see it looks slightly different. That's the only thing I'm saying. So this list of wave numbers on the disk is different from the list of wave numbers on the square.
Yeah, well, that the full spectrum is different. Okay, but you could say, oh, I rescale a bit the circle, or for example, the fact that you have sharp edges.
Mm-hmm.
How do you see it qualitatively on the graph? Is there a way?
But if you have the list, I mean, you see, the point is that you have this list of wave numbers, and you're supposed to have all of it. And from that list, which I think you agree with me that they're different for the disk and the square, from that information you can tell which of the two it was.
Okay, fine. So really, you need to know a lot of information to tell apart.
Exactly. So let me actually advertise another. I mean, precisely because of this objection, you could say that, well, you never have this information available, all of this information. So what I'm doing in the last few years in collaboration with Alain Kohn is to kind of tell what kind of geometry do you get when you only restrict to part of the spectrum. Can you still kind of hear the shape if you only kind of have a limited amount of information available? What can you say about the original shape you started with? Because of course, this infinite number of wave numbers, you will never have it in practice. I mean, speaking physically. So so we develop a mathematical formalism for that that is in the paper that appeared last year. And so we're still working on this, but that's sort of beyond the scope, at least of these lectures, but it's a good point. So thanks for that. And I hope it answered the question. I mean, in any case, I mean, the answer is no. So so there are isospectral domains. So that means that they sound the same, but they are different. Actually, they're not isometrical. And so what happens is that that here is depicted the shapes left and right, and also the vibrational patterns are listed, and they are actually well, what is possible is that of course they vibrate in a different manner, but the wave numbers, they're equal. So there you can actually move from left to right picture by transforming the vibrational pattern that you see from the left to the right in a way that doesn't change the wave number. So answer to Koch is no. Of course, it's interesting to see that these are actually not convex. So these domains, so it's still not clear whether this could work for convex domains. But in any case, it's for instance, there's a nice paper that one could consult. Is that that's in the I think the notices of the AMS a few years ago. Is that if you know it's a triangle of whatever shape, but you know it's in the class of triangles, then it's actually possible to reconstruct the geometry of the triangle from its vibrational spectrum. And then it's actually sufficient to know only the asymptotics. Again, I mean, one has to know the asymptotics, which means you have to know all of the spectrum, but it's possible. Okay, but in general, the answer is no. But in any case, let us continue the story, and let's put a little bit more kind of details, mathematical details into it. So, oh yeah, sorry, this I just said in words. So you can actually get some information from the spectrum, and so I said already that for triangles this already helps a lot in determining the shape. But in general, what happens is that you can look at the number of wave numbers up to a certain scale lambda, which is some cutoff. Then there's a law of Weil that tells you that that number is asymptotically, so the leading asymptotic it's as lambda to the d, and this is what we already saw for the disk and the square, so the two-dimensional, and the parabolic shape of these plots that I depicted. that is kind of confirmation of that fact. So that's something you can get from the spectrum, from the asymptotics actually of the spectrum. You can get some information about the geometry, in particular its dimension.
Excuse me, shouldn't lambda be raised to the power 1 over d?
No, it's a good point, but I'm counting the number of wave numbers up to lambda. So it's not.
I see.
So it's
Okay.
it's good to keep you all sharp because it's the square root, so it's the inverse essentially. Yeah, but a very good point. Thanks.
Okay, thank you.
Yeah, thanks. Okay, let's try to build a little bit the theory behind these wave numbers. So, so in particular, the list of k's that I'm after. So for one thing, I have k squared in this Helmholtz equation, but I am actually interested in k. So these eigenvalues k. So what I could say is that I'm interested in taking the square root of these the eigenvalues in this equation. So I would like to take the square root of this of the Laplacian. Now, of course, one can try to take a square root in a sort of functional analytical manner, but I would like to take one which is still kind of computable and is a first order operator. So it's actually, well, I could say easier to solve, but it's just something that is easier to write down. It's a first order differential operator. So that one is called the Dirac operator. And here you see Paul Dirac. And so his motivation was not so much to try to hear the shape of a drum and actually try to find these wave numbers k for this reason, because this question was not even around. His point was that, and that's also something maybe good to kind of write down, is that Dirac was motivated by finding a relativistic version of the Schrödinger's equation. So version, sorry. And the Schrödinger equation has an interesting structure, is that it's a DDT of a wave function, actually of both x and t. So let me write that x and t. Sorry for this. X and t. And then you have well, your Laplacian, that's maybe in flat space, and there's some v x comma t. There's some potential, some perturbation, if you wish, x comma t. And now the problem is that if you think about space-time, if there's supposed to be some symmetry between space and time, then this one here is first order, whereas this one is second order in the derivatives. So that's the first order differential operator, and this is second order. And this mismatch is kind of the reason that this one is not relativistically invariant, let alone this v. So even if we forget the v for the moment, just put it to 0, this one is just not relativistic. So what would be interesting to take a square root on the right-hand side to write something which is of first order differential equation for a wave function. And this is what Paul Dirac did, motivated, of course, early on already, 1920s, by quantum mechanics, but also knowing that relativistic invariance was an important ingredient for writing down physical theories. So that's kind of maybe another motivation for trying to find such Dirac operators. So let's look at some examples. This will be very basic, but it's illustrative to tell this story like this, I think. So let's start with a circle, or actually you could take R if you wish, the real line. So that's the first example. Then you look at Laplacian on the circle. And for me, Laplacians, as you saw, they were like eigenvalues k squared. So this operator should be positive. You might know that if I write down something like, let me write it as ddt. I write it like this, then I'm supposed to put a minus sign to make this operator positive. It's just something to do with, well, to check symmetry and positivity of this operator. That's not so difficult. Then what I'm supposed to do, of course, the candidate for the first order operator, which is d of S1, that squares to this Laplacian is something like d dt. I mean, that's the only thing I can do. And to take a square root of -1, I also know what to do. It's to put an I. So the complex number I allows me to write down an operator that squares to the Laplacian. So then ds1 squared is actually delta S1. All right, so that's just to get started. And let's now look at a second example, which is T2. That's already interesting, more interesting. R2 works the same, but I try to work with compact manifolds. So it's 2 copies of S1. And now my delta of T2 is now this one, is partial derivatives. And it has this structure, so it's minus in front of the partial derivatives squared. T1 and T2 are the coordinates of the torus. So they're like from 0 to 2 pi, if you wish, or they're rescaled, whatever you want. And then to take a square root, let's try. So a candidate would be something like, T1, T2, no. This is supposed to be something which is, well, there's only 2 possibilities, dt1, dt2. And let me put something in front, just as I did before. I have some a and a b, and I'm supposed to solve the equation that the square of this operator is the Laplacian. So for that to be true, I need a squared is equal to, well, I need to be -1. Then I have some cross term, which is AB. So that's supposed to be actually, if I look at the Laplacian here, then I see that there's no such term. So this cross term has to be 0. 2AB has to be 0. And also B squared has to be -1. Now you can look a long time at these formulas, but it's not too difficult to understand. There's no such solution, zero divisor that also solves that it squares to -1. So this is not going to work. And of course, then it was Dirac's insight to think beyond these numbers. Already before I had to think beyond real numbers and put in an I. Now I have to think beyond that as well. And what you can do is you can instead take A to be a matrix, to check for the right order, and this one is like that. And then, so these matrices A and B, they anti-commute, which means exactly that their cross term will vanish. So they will satisfy AB plus BA. Of course, I have to take into account the fact that they do not commute. AB plus BA is 0, and A squares to minus the identity, and so does B squared. So these matrices, they actually work. And it tells me that the Dirac operator on the 2 torus is not a differential operator of order 1 in the usual sense, but the coefficients are matrix values. So what you find is that you have a 0 ddt1 plus I ddt2 minus ddt1 plus I ddt2. So that's a symmetric in a sense, again with the minus sign as for the thing I just explained for the circle. So this is it's actually a symmetric operator. It's even essentially self-adjoint on a suitable domain. I will not go into too much details of that type, because that's not the kind of conference we're at. Here and there it will enter, but and of course the formalism, the field is based very heavily on functional analysis, but I try to kind of maneuver through it kind of lightly. So then you find actually that the square is the Laplacian times a 2x2 identity matrix. Then there's still another kind of final example, but it continues like this, but it's interesting to just write it out. So there's a 4 torus. Then you just have Of course, there's T3 and T4 as well, and they just sum up like that. And it looks almost impossible that if you write down something like D T4 as A DDT1 plus B DDT2 plus C DDT3 plus D DDT4. That it's possible to kind of have all these A, B, C, and D squared to minus some identity, as well as having all these cross terms A times B plus B times A vanish. So they should all anticommute. And this is actually possible. So you can make larger matrices. And in fact, what you can do is the following, and here it's already quite nicely done, is that you can take, to phrase this in terms of quaternions, that this is A is 1, B is I. This is correct. Well, apart from the -1 sign, but one has to kind of C is J. So this I leave you to check in more detail. Now that I write it, of course. So these objects, they will actually multiply to square to the minus the identity. And what happens is that the kind of the appearance of these quaternions that allow me to have these cross terms vanish, they will precisely. Let me actually see how this works. It's the same matrix. So let me actually make this precise, because now I'm giving you something that's not completely correct. So it's A is 0, 1, -1, like this, and all the others, they will appear in the matrix. So that's the idea. So then B is 0, I, C is J, that's the J and the K from the quaternions, K. And they will be precisely the one that are the ingredients, the matrices that are responsible for the fact that all these cross terms will vanish, as well as all their squares will be minus the identity. And so what you find now is that if you think about what happens, so this is also possible with 2x2 matrices, now with values in the quaternions. What you find is that there's an appearance of some kind of algebra going on where you have anti-commutation relations, where in the first case you needed the complex numbers. So that's the first one, that's the one-dimensional case. In 2 dimensions, of course, one can do this in 3 dimensions as well, but in 2 dimensions, we had these 2 matrices, and they will actually generate, if you keep multiplying them, the quaternions themselves. They're like the matrix representation of the quaternions. Whereas here, I take 2x2 matrices with values in the quaternions. So these are the kind of objects that we're looking at, and that are needed to write down the solution that Dirac did. And of course, Dirac did it in 3+1 dimensions in different signatures in Minkowski space, but that doesn't really matter. The point is that it's possible. All right, so in general then, so what happens is that that we find that we need, let's see, yeah, in general we need in general, what we will be needing is something like some anti-commuting matrices, essentially, that that also square to minus the identity. And I showed you some examples. The circle, it's possible. The 2 torus, also on the plane, Euclidean spaces, that all works. 4 torus, that all works. That's all fine. But you could imagine that this is not always possible globally. So to find globally such matrices, so that you can always find this square roots. Now, and indeed there are obstructions. That's another story for which I refer to spin geometry. Any book with the title would probably work, but there's Laws and Michelson, which is in particular the most complete one. This works for Riemannian spin manifolds. And in fact, spin C is just the definition that I will also not explain, but I will tell you what it does. Because then what happens is that in this case, so for this class of manifolds, Riemannian spin C manifolds, then we have, first of all, it's possible to construct a bundle SM, which is like the global version of this vector space on which these matrices act. So these are the so-called spinor bundle on M. There's locally the vectors in actually what I had before was C. Then I had 2 by 2 matrices, C2 and then C4. So this actually continues in any dimension. You can just do this computation, and you find that you need much more space every time you go up one dimension to be able to have all these anti-commutation in place. So these are spinors, and they carry a representation of so-called Clifford algebra. And these are generated by gamma mu. So there are Dirac matrices, also called like that, gamma matrices, satisfying this crucial rule is that gamma mu, gamma nu plus gamma nu, gamma mu is equal to 2 times G mu nu. All right, so that's kind of the ingredient that you need to write such a anti-commutation that I had before. And so these are kind of the defining relations, the relations that are satisfied by the A and the B that I had on the previous slide, and the C and the D as well. So you have these anti-commutations, so they will take care of the fact that the cross terms for G mu nu, the delta, mu nu, the Kronecker delta, S would be the metric for the flat case, the torus. Then you find that they will actually vanish, whereas the square is, in this case, the identity. So up to a factor of I, that will be precisely the one that I need. Now, besides that, I need to be able to take derivatives of these spinors. Now I have partial derivatives, but that's of course not sufficient on a spinor on a bundle. So, which is then presumed to exist because the manifold is spin C. Then I get this. That's called the spin connection. And since I want this relation to hold with the Laplacian, it should somehow be connected to the Levi-Civita connection that you get to define the Laplacian that you get from the metric. So what you find is that, that this is by definition, there's a lift, and I will make this more precise, lift of the Levi-Civita connection on forms or on covector fields. So as you see here, I'm able to kind of Clifford multiply with forms by using this gamma. What you presume or what you assume for the spin connection is that you have this rule that if you do this gamma S, then this is gamma of Levi-Civita on omega of S plus this two. And that's the rule that you need. So for omega, this could be this dx mu. So it's good to think about it like that, locally at least. And S is a section in this, so it's a spinor, as they're called. And
the gamma is the multiplication that I just defined over here in terms of these gamma mu symbols that can be written down locally like this, and of course it should be globally defined to act on these spinors. So these are the ingredients. Lambda LC is the Levi-Civita connection. So these are the kind of the rules that you have for these for this Levi-Civita connection to lift two spinors. Okay, so this is what I did in the example. So I wrote down, of course, the bundle was trivial in that case. I wrote down some partial derivatives. So they're the kind of the spin connection. And then I wrote down these matrices A and B and so forth. And they are kind of representing this Clifford algebra. So what do we do with them? So in general, for this such a spin manifold M, what you find is that that you have possibility to kind of have a Dirac operator. Which is defined as follows. So dm, it takes spinors, so sections of this kind of assumed spinor bundle to itself, and it takes S, and what do? You apply your spin connection, and then you Clifford multiply. You sum over this index mu. So this is kind of a way to get, of course, if you have like a first order differential operator and you want to kind of get rid of the indices, then you have to contract it with something. So for the Laplacian, you contract it with the second differential operator, like the other Levi-Civita connection. But here we cannot do that because I want the first order operator. So this is possible if I'm in a situation that I have these spinors, of which I can take derivatives, and then Clifford multiply them to contract the index gamma mu. So that's called the Dirac operator, and it exists on spin C, and it is unique on, in this sense, on spin manifolds. And uniqueness is it's related to the fact that there's an ambiguity in this spin lift, that you can of course lift it in several ways, and there are many possibilities to lift it for spin C. But for spin manifolds, there's an additional assumption that makes it unique. But that's also not so much of the problem. It's just that it's possible for a certain class of Riemannian manifolds to write down such an operator, such a Dirac operator. And then the result that kind of confirms what I was after, that I said I want to have like a square root of a Laplacian that is true up to 0th order correction. So that's this formula, which is a nice one. So it tells you that on any spin C manifold, there is this possibility to take a square root up to sort of a defect, which is this defect is precisely the curvature. So that's the scalar curvature times 1/4. So that's also an interesting starting point for a discussion, is that usually curvature arises as a defect of something, like with principal bundles, it's a defect of some map to be a Lie algebra map. And here you see that it's precisely the defect of this formula to hold. That's the curvature. And of course, we didn't see that in the flat case for the tori, for instance, or also for the Euclidean spaces, but it's there in general. So that's actually not so bad. I mean, it's also something which is positive, that you have this possibility to detect curvature in this way. Okay, so let's look a little bit ahead. So what do I need?
Yeah, there's maybe a few things that I could say about the spectrum at this point. Spectrum of dm. So if m is compact, then, which I assumed throughout, then dm is actually on this sections, these smooth sections of the spinor bundle, is an essentially self-adjoint operator with compacts. So that's on, of course, tell you the domain on these spinors with compact resolvents. And that means that the, and that's actually important in view of the question already asked before, is that means that the eigenvalues of dm, they accumulate only at infinity. And they actually do accumulate at infinity in the infinite dimensional case, which for manifolds you will always have. So this means that that I have some kind of list. I can write it like this in this notation, that I can kind of take these are the rank 1 projections here on the eigenvector psi n multiplied by lambda n. So these are the elements in the spectrum. These are the eigenvalues. And now the question is, so these are the wave numbers, if you wish. These lambda n, this list, this will accumulate at infinity, but it's discrete and real. So that's all due to the fact that so this lambda n is in the real numbers, accumulates only at infinity, so it cannot accumulate anywhere else. And this is precisely the thing that that is captured by these kind of functional analytical phrasing, that it's self-adjoint operator, it's compact resolvent. That's precisely phrasing this. And that's also the passage to non-commutative geometry, which I will do in a moment, is that this kind of information that you have now, by looking at an operator like this, but maybe forgetting about the fact that it came from a manifold or a spin C manifold, that's the starting point of non-commutative geometry, because then you can allow other structures to appear, which are not coming from a manifold, but still can be captured in the same way, the still kind of spectral way as the manifolds were, even though they're not at all related to a manifold, but maybe to some non-commutative space. So this will be the motivation to. In any case, to come back to the question of Koch, I mean, even if I have these lambda n's, even if I have these discrete numbers, these lambda n's, then still I know that I cannot go back to M, because there is these counterexamples. So in principle, it's not sufficient to know the spectrum. And in fact, it is true that you need additional information, which I would like to kind of phrase, if I use this kind of metaphor of Koch, is that it's like you're not listening to the shape, you're not kind of hearing the shape, but you're sort of locally hearing the shape. So you try to listen locally to the shape, and then actually you can patch these pieces together to get a manifold. And this is what is done in non-commutative geometry. That's the next slide, which is pre-prepared, which is this one. So in non-commutative geometry, you get the following. So instead of just working with this dm, this here, I combine it with an algebra of coordinate functions, C of m, continuous functions. So these are continuous functions from m to c. So that's an algebra, because you can multiply them pointwise. It's and also added pointwise. And there's also a norm, which is the supremum norm. So it's in fact a C-star algebra. This is not so much the topic of this conference, even though in Münster there's so much expertise on this that it's easy to get information about that even during this week, probably. So I don't see so much of a problem there, and I will probably also kind of avoid going into too many details on that. But if you do the combination of Cm with Dm, then you can actually do the reconstruction of M, G. So, of course, one should keep in mind that this Cm, or inside you find C infinity of M, the smooth functions on from M to C. So how do they kind of communicate? So you have the C infinity of M, and you have this Dirac operator on M. And this Dirac operator is an operator, by definition, on these spinors. So I have to kind of find a common place for them to meet, which is, so they kind of meets dm by acting on the same Hilbert space. So this is on Sm, which sits in the Hilbert space of L2 spinors. Okay, so there's some additional ingredient that is necessary. For now, it's just sufficient to think about these smooth sections on Sm, of Sm on M. And so both of them, they will act on this, this space, and they do so by, for instance, let me write it down. So dm, of course, is by definition an operator on this space. But here I also have multiplication with the function, which is fs. Well, what can you do? F is a function from M to C. S is locally a function from M to the spinor bundle. So what I can do is I just multiply them pointwise. So what I get is I get F times S, which is just taking a point P, and it maps it to F of P, S of P. And that's my new section, and that's how C infinity of M acts on this, these spinors. And this actually extends to operators on L2 Sm. Okay, so there's this other possibility to have operators acting on L2 of Sm. They are given by scalar functions actually, and that's how they kind of meet each other. And from that data, it's possible to reconstruct the manifold, and including the metric G. So the geometry is actually then really captured by this combination of ingredients of the C-star algebra. Then there's this Dirac operator dm, and they are combined in this Hilbert space L2 of Sm. So I will give
a question.
Yeah.
So you are referring to the theorem which is in this paper, which was called, I think, CKM invariant, yes? Because there is also the reconstruction theorem for commutative spectral triples, but it is much more difficult, as I recall.
It's the latter one. So it's I think it's called the spectral characterization of manifolds, something like this. So it's not the one of CKM. That's different, but it's very much in that line. So CKM is an invariant that you kind of associate to this pair that I wrote down here of C of M and dm, and it tells you how, I mean, how they sit relative to each other. That's sort of the idea. And once you know that, you can kind of realize it as operators on L2 and so on. And then you can do the reconstruction. But that one is in the paper, which is called Spectral Characterization of Riemannian spin manifolds, something like this.
Okay, thank you. But what I've meant is that you are referring to the theorem which is, in which you start with the algebra of function on the manifold, not with general commutative spectral triple, which is much more difficult, yes?
Sure. So that's a very good point. So in '96, so what I'm referring to here in 2008 is when you only know, so it's the actual reconstruction, that you know you have a commutative C-star algebra, and a combination of data as I write here. And from that, you try to reconstruct a manifold on which the data was a Dirac operator, etc. Of course, in '96, and this is what you're referring to, there was also a result that stated that if you know that you are on C infinity of M, then you can reconstruct the manifold from dm and so on and so on. And you can actually realize that the Dirac operator that satisfies suitable kind of conditions, that is actually Dirac operator in the sense I just described. But it's indeed a nuance whether you know that M is a manifold or not already. Does that help?
Yes. Thank you.
All right, thanks. So let me only, since I think I have about 10 minutes or so, please correct me if I'm wrong. I would like to do one thing to kind of illustrate how this all kind of how this goes. So
Walter.
Yeah.
When you mean reconstruction, I suppose you mean up to isometries, up to something.
Sure. So it's up to also it's well, they should be liftable. So it's kind of spin isometries if you to make it precise. Is that clear? So because you also need to kind of take into account that you have a spin structure. So you would like to actually reconstruct that spin structure in addition to the fact that you reconstruct a manifold with a Riemannian structure for which you would need isometries. Yeah. There could be different spin structures or spin C structures on the same Riemannian manifold. And if you try to kind of, that's also captured. You can actually reconstruct, in this case, you actually reconstruct the bundle SM, and that's already sufficient to kind of give you back the spin C structure. Okay, thanks for these questions. So then let's start with the data. This will also be my final action of today. So I said I have C infinity of M, and I combine it with L2 of SM. I will now write it in a more conventional way, and I have DM. Okay, and this is a triple, soon to be called spectral triple, because it's kind of the spectral data that I associate to M, G with the spin C structure, and the ingredients I already explained to you, so they act on this Hilbert space here and there. Now, what I try to explain to you now is how to get from this. Well, I won't explain this because it's to get to M is very difficult, to get to the manifold M. But let me explain to you how would it be possible to get like metric structure on M. Suppose that we know that there's some kind of underlying manifold M. And of course, the construction of M, that's the most challenging part. And that was only done in 2008. So that's what I was referring to. So M, G. So what I will do is I will try to kind of, first of all, get a metric or a distance function on the points on M, which is only defined in terms of these three ingredients on the left-hand side. Okay, so that's what I will call D, like this. How should I call it? Just D, and I'll try to compare it with the distance function dg that I get from the metric. So what I will do is I have to write a formula that is only defined in terms of the ingredients. So I take a supremum, I take f of x minus f of y. Then I have to kind of, so what I try to do is I want to measure the distance between 2 points x and y, but I will transfer this distance into function space. And this I can do if I take like an upper bound on what I could call the gradient. So it's the norm of the, so the operator norm of the commutator of dm with f. And since dm is the first order operator, I'm just taking like derivatives. What you actually find, so this is something like gamma mu d mu f, that this is actually just the Lipschitz norm of f. So it's like the smallest Lipschitz constant for the function f. Now that's a little computation, which I won't do, but it's actually doable. I will refer to my book or Elements of Non-commutative Geometry. That's another source for that. Now, first of all, you find that this is a metric on M, and actually my claim or the claim, which that dates back to the 1990s, is that this distance, so this you can already find in the book of Const, that this distance that I just defined on points of M in terms of the data that I was given, like functions and so on, and the Dirac operator dm, that distance is equal to the distance function that you get by taking what you do, like the infimum of the length of paths on my space, using the metric, like this. Where you start at x and you end at y. Let me not write it for a moment. So now what happens is to prove this, it's actually quite, it's not so difficult. I mean, there's a few technicalities, of course, which I won't touch upon, is that if you know that this commutator bound of dm with f is smaller or equal to 1, you know that the Lipschitz constant is smaller or equal to 1. So this means that if I look at this dx comma y, then it's since it's the supremum over all these functions with that property, f of x minus f of y is of course, so f of x minus f of y is smaller or equal to x minus y, so the distance, sorry, between them, because of the fact that I take this Lipschitz constant to be 1, it's precisely this. So this already tells me that if I take the supremum, it doesn't really matter, it's always smaller or equal to that one. And since I know that my f satisfies the property that here it's written 1, Lipschitz constant is just, or smaller or equal to 1 actually. Now for a fixed y, what you can do, you can attain this upper bound by taking a special kind of function, by taking f of x to be dg x comma y. Okay, so what you do is you just fix your y, and now what I want to do is I want to kind of have a function for which this supremum is then of course larger, and for that function you already attain this dg, and what you just do is you just look at the function which just measures how far away you are from y using the metric. And there are some subtleties here about this not being smooth and so on, and so there are some problems in its formulation, but one can easily kind of fix this. One can work around that, and then that actually works. And that means that from this data of these three ingredients, I can derive, supposing that I have a manifold M, I can derive this distance, the Riemannian distance, by looking at this formula. And this distance function is called the Const distance function. Actually, that's the generalization where you kind of try to interpret what you write over here, f of x minus f of y. So it's a special case of that Const distance function where you look at states. So that, but that's a more general situation. So what I want to end with is giving you the definition of the general ingredients for doing non-commutative geometry, and then I will stop because that will be the starting point for tomorrow, and it will give you some time to kind of digest all of this. So I have this kind of spectrally defined triple, like the one on top of C infinity of M, L2, and dm. But what I will do now is I take a more general algebra, Hilbert space, and an unbounded operator D. And what I will assume is that A, that's a star algebra. Also there you can avoid to work with C-star algebras, even though they are bounded operators. So of course we're very close to C-star algebras. H is just some Hilbert space. And so carrying a representation, yeah, so I already said that on a H Hilbert space. D, that's essentially self-adjoint operator in H. And then there are two kind of conditions that one can extract from the kind of the example, is that first of all, the commutator D and A is bounded or extends to a bounded commutator for all A in A. So that's like being first order. And then also that this this resolvent, let me write it like this, just for convenience, is compact. It's a compact operator. So that means that being compact means that the eigenvalues would accumulate, can only accumulate at 0. So I mean the other way around, that the eigenvalues of D, they will accumulate at infinity. And that's the kind of the setup of non-commutative geometry. And that will also be the kind of the starting point for tomorrow, where we look into examples. First of all, we look into gauge theories. I will give you more examples, which are non-commutative. It will also build towards these matrix models. But for now, this was the motivation coming from geometry, taking a spectral viewpoint and getting to this kind of spectral notion of geometry. This is the spectral triple. Okay, thank you very much for your attention. And questions are more than welcome, of course.
Okay. Thanks a lot, Walter. I think this worked. Right. Okay, questions.
So how do you get the space and sort of a distance? So you mentioned the generalization of this formula. Can you maybe say a word on this?
Yeah, so let me add a page here. Tomorrow I'll try to do this beforehand. I think it's easier. So yeah, so the idea is that if you're in this situation of AHD, then this this is a star algebra of bounded operators. So what you could say is that this sits in a C-star algebra A, which is also called A, but it's not calligraphic anymore, so it's kind of straight. And for that you have states. So actually, let me call that S of A. It's the state space. They're like positive linear functionals of norm 1. And they're defined because we're in the context of a C-star algebra. And actually that's compact, and there's by convexity, I mean, there's this notion of extreme points. So what you can look at is the pure state space of A. These are the extremal points of this state space. And they're kind of the geometry, they capture the geometry of the space, even though it could be very meager. So I would advocate to look at the algebra, but the state space also captures some information, and in fact tells us something like the classical underlying space of this algebra. And for just to give you the example, S of C of M, that's what these are all positive linear functionals of a given norm. So they're like Borel measures, regular Borel measures on M. And P of C of M, they're like the point measures, or really just the points of M, including the topology. So that's something quite comforting, is that you can kind of get back to M, and this is the way you get back to M if you are given this triple. So as a topological space, okay? So not a manifold, that's the difficult part, which I will not explain, but these are the points of M. And what you can then do is either you take states phi and psi, or you take pure states, doesn't really matter. So maybe here, just to say that the state of F is F evaluated at X. But the point is, and this was your question, is that if I'm in this context of a spectral triple, but no relation to some manifold, then I can still write down this formula. So I can take the supremum over all elements in A. I evaluate my state at A, the other state also at A. And then I impose the fact that this commutator, which was bounded, is actually bound smaller or equal to 1. And this is the distance formula of Const. And it generalizes the Riemannian distance in the case of a manifold, and you take pure states. And for Borel measures, there's also a Mons-Kantorowicz distance, which is then actually generalized by the same formula. So it's precisely the idea that you try to optimize or extremize something under a constraint. And this is very much in the spirit of Mons-Kantorowicz distance, is that you have some cost function which is limited, and then you try to kind of extremize just a convex optimization problem that you try to solve to compute this. And I think this will come back later on during the week, maybe tomorrow afternoon in some of the talks. But this is the kind of the distance formula that you can write down for arbitrary states in the context of a spectral triple. Does that answer the question?
It could happen that the distance is infinity, yes?
Exactly, yeah. So it's a very good point, yeah. It's an extended metric. So, and
okay.
Yeah, so that's and in fact it's an interesting problem, because if you think about what you have as a state space, then that would be kind of weakly star compact, typically in a unital case, for instance. And apparently, one has to impose this compatibility between these topologies, because now I have a topology by this distance on my state space, which is not necessarily the same as the one I'm given like from one general approach by looking at the weak star topology. So that's a condition that is also added in, for instance, the work of Riefel, maybe good to mention this, on compact, so quantum compact metric spaces, where that's an additional assumption, but it's very hard to check. So it's not so clear what assumptions do you need on D or A for this metric to capture the weak star topology that you're given on the state space to start with. Yeah, it's a very good point. Thanks.
More questions?
Maybe I have just one more question. Could we please go back to the slide with isospectral shapes?
Yeah.
So these are two examples, yes? From the left-hand side, we have the same shape, but you somehow wanted to visualize the frequencies, yes?
That's right. So this is the shape 1, the one with the, and this is shape 2, or the boundary of shape 2. So it is one example of a sort of one example of two isospectral domains. And this is frequency lambda 1, this is frequency lambda 2, and this is lambda 3, and they're the same for, say, shape 1 has the same frequency list as shape 2. Of course, the solution is different because the shape is different. So the vibrational pattern should be kind of transformed from shape 1 to shape 2, or vice versa, but the frequency remains the same. And there's a very nice kind of elementary passage from going from one to the other, which one can write down. Hope that answers the question.
Okay, but maybe just one more stupid question. So this example is from 92. So this suggests that this is not so easy to find those examples. On the other hand, these shapes are very simple in R2. So what is the difficulty? Why people hadn't figured this out before?
Well, it's actually at the time that Mark Kac wrote this paper, it was more or less clear that it was the answer was no, but the examples, they were higher dimensional. So in general, it's not so difficult. I think there's classes of examples of group actions that can be easily, well, I mean, easily constructed in the sense that you can write down a whole class of families, which will work. But in the planar domain, it's more difficult. But there's also other possibilities that you can write down, which are not convex, but they're not connected, for instance. So there are many more examples, also more recent. But it's just that to find examples may not be so difficult. There's also, I think, some kind of mill, I don't know how it's called, but it's some kind of mill configuration that you can easily write down, always non-convex. But the problem is to do the other way. So to for instance, find convex domains and maybe show it for them. So there's some progress, but that's very kind of slow in a sense. So I told you about triangles. So if you know it's a triangle,
Exactly.
you can reconstruct. But higher than that, I mean, it's very complicated.
Okay, thank you.
May I make a simple remark?
Yeah, Harold, hi.
Hi, Walter. Very nice conference. I don't know, in 56 or so, Milnor found two cubes, which are root lattices, 16-dimensional ones.
Mm-hmm.
Root lattices of E8 cross E8 and SO16 or so, which enter in strings, by the way. So, just a remark.
There were the examples that I was indeed referring to that Kac already, I guess he already knew because he also cites this work in this.
Oh, I see. Okay.
Yeah, so it was clear that, but then the question was still remaining whether this could work in the plane.
Yeah, sure. No,
yeah.
okay.
Yeah, sure. No, very good point. Milnor was the one that gave these
these examples already.
This was in one-page paper, yes?
Exactly, this one.
Good. Thanks a lot, Walter. I think everyone is happy.